So I was talking about the complex programmable logic devices. When we have to implement an application, a circuit which requires more number of inputs, more number of outputs. So during that time, uh, the number of inputs and outputs and the product terms available in a PLA or PAL that are commercially available may not be sufficient. We may be requiring a large number of inputs to be implemented and large number of outputs we require, including the large number of product terms. So the simple, the PLDs that are generally available in the market, they are called simple PLDs or SPLDs. Now we have one option. We can cascade. We can, connect multiple number of SPLDs. For example, when we implement certain logic in one PLD, the output and the output of this and the rest of the inputs we can connect to another SPLD, and if we require more, we can do such cascading continuously to increase the size of the circuit. But what will happen? Each SPLD is having is available in the form of IC. So the number of ICs that we require to put in the PCB increases. So that increases the size of the PCB, and which also increases the power consumption, and area and weight of the that circuit and the appliance will also be larger, so which will be unattractive uh, from the market point of view. So the researcher has come out of the solution, come out of the problem and provide a solution that why not to house such SPLDs inside an IC, where in the inside this IC there will be number of SPLDs, and there will be a common connection uh, that also available inside the IC. So now, for example, 16 or 32 number of SPLDs can be housed in one IC, inside one IC. So if we have large number of input output requirements, we in such situation we do not have to use so many ICs. One IC probably is going to solve our problem, because within the IC we will be getting huge number of logic resources, huge number of the PLDs, and if we require to interconnect, that means the output of one PLD to be connected as input of the another PLD. So that also we can do internally through programming. So this has been a wonderful solution for increasing need of inputs and output to be implemented to design a digital system. Now, this device, which houses multiple number of SPLDs within it and provide the interconnection between them, is called the complex programmable logic device. I will show you the diagram in the next slide. See, it consists of a number of pair-like blocks. Now, these pair-like blocks are referred as, they are given the name of logic block, input output blocks, and the set of interconnection wires called interconnection switch matrix. So the logic blocks are connected to the interconnection switch matrix, and each of the logic block is also connected to an IO block, to which a number of chips input and output pins are attached. So whatever the textual lines are there, that I will be explaining in my next slide with the help of the diagram. So you can see that this is the diagram of generic diagram of a CPLD, complex programmable logic device. So over here you can see that this is one, you can think that this is one PLD, this is another PLD, this is third PLD, this is fourth PLD. but this is only a symbolic representation. We can house 16 number of PLDs, we can house 32 number of PLD if required inside one CPLD IC. Now, this SPLD, suppose it is implementing certain logic functions, but whatever system we are trying to design uh, is not sufficient to be housed in this block. So in that case, what we can do, we can take more number of logic blocks where certain portion of the logic is implemented here, another portion is implemented over here, third portion is implemented over here, and so on. In case the output of this block is required as input for this, so in this way you can get the feedback from here, and this can be given as logic input to this block. So this way we can expand it to a great extent, and we can implement our the requirement of large input outputs and large logic circuit uh, suitably. Now you see, in PLDs, we have seen there are certain inputs, like we have other day we have seen PL 16, L 18. So that was having maximum 16 number of inputs, maximum 8 number of outputs. So these are the inputs, and these are the outputs. And this MC0, MC1, MCX, they represent actually the macro cell. Regarding macro cell, functioning of macro cell, in the previous day class we had elaborate discussion. So similar type of macro cells are located in these PLDs, so that we can implement uh, sequential logics as well as combinational logic as per our requirement. So the output of this, if it is not sufficient to implement over here, the output can be feedback, and this feedback can be given as input to another block to expand this. Now, apart from that, suppose the output that is generated from this block, if it has to be sent to the outside the world, that means outside the IC, then through this line and through these IO pins, you can send it to the outside. Similarly, in this provision is there in all the PLDs inside this CPLD. Now, how to connect these CPLD with the external world so that they can receive inputs from the outside of the CPLD. So this is the IO pins, this is the IO block which receives external input through this, and this input will come as this, and it will go to this interconnection switch matrix. And through this interconnection switch matrix, you can feed the inputs to this logic block, you can feed the inputs to the logic block wherever, whatever way you like to direct them, route them, you can do so. So output from external circuit, external inputs will be fed to this CPLD through these IO blocks, and first they will come this way, and based on these are interconnect switch metric, means they are programmable routing channel. So what I will explain in FPGA section in today's class about the interconnection switch matrix in details. uh, so these are nothing but routing channels, so they are capable of connecting this input to this, or this input to this input to somewhere else as per your requirement through programming. And how programming we do, that we have learned in our practical classes on FPGA. We have used Quartus software, and when Quartus software is downloaded in the FPGA board DE2E150, we have seen that our program is downloaded. So during that time, this uh, interconnection matrix, switch matrices are being programmed. Now, this is the structure of the CPLD. So if I will stop for a while and get your feedback if you have any difficulty in understanding this particular part, internal structure of CPLD, architecture of CPLD, so that I can answer your queries. So I am unmuting all of you. Now I have just discussed about the CPLD. If you have got any doubt, if you have not understood about CPLD, you can raise your doubts. Yes. Hello. I have discussed about CPLD, right? Our internal architecture of CPLD. If you have got any doubt, you can ask me, or otherwise I will proceed to the next, section. Anybody having any doubt? CPLD? No? Should I proceed? You tell me.
Yes, sir. Proceed.
Okay. So thank you then. I'm muting you once again. So we have understood the internal structure of CPLD. Now we will proceed to the next type of technology in digital system design, and we have learned little bit about field programmable gate array, that is FPGA, from our initial classes. I have discussed about this, and we did some practical classes on FPGA as well. So this is the formal theory class where we will discuss about FPGA. Now you see, CPLD was very good compared to PLDs because it can implement large amount of logic resources inside it, logic functions inside it. So certain applications can be developed inside the CPLD. But again, the increasing need of, because we people are not satisfied with what we are getting, so we want more devices, high speed and power efficient, low cost devices. As our requirement grows, the challenge to the researcher is also growing, and the complexity of the circuits are increasing day by day. So a time has come that when a digital system is to be designed, even the architecture of CPLD is not enough in many cases to cater our need. Now CPLD has got certain limitation. You see, CPLD architecture beyond the logic density of 10,000 equivalent gates become very difficult. The reason is the interconnection complexity, because the interconnection matrix that we have seen in the middle of the CPLD block, it becomes so complex that managing it is a Herculean task. So people have thought of alternative architecture, that we have to cater the need of large number of inputs, large number of outputs, large number of product terms, but such requirement in many cases CPLD is not able to cater. So they thought about alternative architecture, and the alternative architecture is our field programmable gate array, which we popularly call as FPGA. So FPGAs are digital integrated circuit. They are IC only, that contain configurable blocks of logic along with configurable interconnections. Between these blocks, the logic densities of FPGA ranges from typically 2000 to as high as 50,000 gates, and even more in newer chips. Now, what is this logic density? Let me explain to you. See, we know that NAND gate and NOR gate are universal gate. So NAND gate, especially I'm talking about NAND gate, we can design any circuit using only NAND gate. That's why it is called universal gate. So in digital system design, we measure the logic densities in terms of the equivalent NAND gates. That means in order to implement a Boolean function or an application, what is the maximum number of equivalent NAND gates are required. So that is called the logic requirement. So FPGA can house, the small FPGA can house as minimum as 2000 number of uh, I mean NAND gates and as high as 50,000 gates. But this data is also relatively older. Now newer chips, newer FPGA chips, they offer huge amount of such logic density. So you see the architecture of FPGA is like this. In case of CPLD, if we compare with FPGA, in CPLD we have seen inside CPLD we have got PLDs, certain number of PLDs. So these PLDs can implement a certain amount of logic functions or Boolean expressions within it. But here, in case of FPGA, we will see only small block, because this block, it can implement a very small logic function. This logic function I can describe as programmable logic block. This has been given the name PLB, programmable logic block. So I will show you what is inside it in the subsequent slide. Now this logic block, as I told, can implement a very small logic function of maybe 4 input or 5 input at the most, or in newer FPGAs this can be slightly more. Now these are called horizontal routing channel and these are called vertical routing channel. Why we require this horizontal and vertical routing channel is that since these logic blocks, program PLBs, implement very small amount of logic, so one block is not enough. We may require a large number of blocks, but the output of this block may be to be fed as input to this one, and in output of this we may require to feed as input of this. So how we can accomplish this task? This is through this routing channel. The output of this may be given here and that may go as input to this. Output of this may come as this. So this may go as output and go input as like this. So all this can be, all this routing, this is called routing. This routing can be done through programming, and in Qualta software or in Xilinx Vivado software, it is done automatically because there are certain algorithms designed by the researchers. So whenever we do such, whenever we download such programs on FPGA, so this routing is automatically done. We need not have to bother. But those who study VLSI, especially in master degree level, they have to study about this in details. Now, I was talking about the horizontal and routing, horizontal and vertical routing channel. As I told, the function of horizontal and vertical routing channel is to interconnect the output of certain blocks to the input of these another block, so that the desired logic function can be implemented. Now, again, FPGA is a IC. So this IC has to receive external inputs, and whatever has been processed within this has to send to the outside world. So for that purpose, we need IO blocks, we need IO pins. So these blocks which are surrounding the FPGA, these are called input-output blocks through which we can receive, rather the FPGA can receive input from external world and can send output to the external world to receive, transfer the signal to the other parts of the circuit. So this is the basic block diagram of a FPGA. Next, we will go into the programmable logic block in the next slide. So you can see that this is the structure of our programmable logic block, which we have seen in the previous slide. So this is, you can think that 4 input LUT. So you can also think that this LUT means, LUT stands for lookup table. So you can also think that this is a multiplexer. We know that multiplexer are referred to as universal logic circuit because multiplexers can implement any type of Boolean function within it. So this is a 16:1 marks. Understand? This is a 16:1 marks where A, B, C, D are the select inputs. So any Boolean function of 4 variable can be implemented inside this LUT, inside this multiplexer. Now the output of this will be a combinational one. So if you want a combinational expression to be implemented of 4 input, so that can be housed here, and the output will be directly available in the Y output. And if you if you want, suppose the sequential output, so in that case you will have to use this flip-flop. So if you have to use this flip-flop, then you will have to use this marks. You will have to make this active marks input active, so that this output through this marks will go to the flip-flop, and the data will be stored in this flip-flop. So the stored data through its Q input will be available out in the output. So uh, what is Y? What is Q? Y is the combinational output of the 4 input LUT or marks, and Q is the sequential output of this same marks or LUT. Now with the help of this marks, a provision has been created that there in some situation you do not require to use this flip-flop. Suppose your uh, expression is combinational. So if your expression is combinational, you implement that circuit over here, and the combinational output is available here. So inside this block, since this flip-flop is there, so this flip-flop will not be used. So the designer, in order to optimize the use of the circuit, use of the resources available inside the FPGAs or logic blocks, what they have done, they have kept an extra provision. Suppose uh, there may be in the adjacent block, there may be requirement of one more flip-flop. So this flip-flop can be used by that, for which the input may come through E, and this multiplexer in that situation will route this input to the output, and it can be stored over here, and its output in sequential form, stored output will be available in the queue. So this provision increases the efficiency or uses of the logic resources inside the FPGA. So whenever we talk about flip-flop, flip-flop is a sequential circuit. It requires a clock. So this is the external clock to be applied in the programmable logic block. I hope you have understood about the programmable logic block and how it works. Next is the input-output block. See, in this diagram, we have seen about the I/O block. Next, I am going to describe about the I/O block inside it, how its structure is in this slide. So you can see that this I/O block, this is the entire I/O block. So I/O block consists of this portion as well as the I/O pins. Now we have seen, even in case of PL16 L8, we have seen there are certain pins which can perform dual function, input as well as output, right? So, but at a time only one function it performs. If you want it to work as input, it will work only as input. If you want it to work as output, it will work only as output. So for example, suppose this pin you want to work it as output. So in that case, what will happen? This control unit, this control signal will be high. So if it is high, then this buffer, this inverter is a tri-state inverter. So if it is control is 1, in that case it will act as an inverter. So whatever is the output coming to its input will be inverted and will be supplied to the external circuit through this IO pin. So this is the out functioning of the output mode. Now, when it works as input, during that time the control will be 0. So if control is 0, then this inverter will be in tri-state. So whatever input you apply to here, so nothing will go to the output of this. So this path virtually as if it is connected. So no current will flow from this side. So during that time, this pin will work as input pin. So signal coming from external input will come through this pin and it will pass through the buffer and it will go to the input circuit. So this is the function of the input output block. Next, I will talk about the programmable interconnect. So programmable interconnect, let me go to the again this diagram. So we are going to talk about now the horizontal and vertical routing channels. So these are our horizontal routing channels and these are our vertical routing channels. These are our logic blocks. Now in this diagram, since we are going to understand the functioning and arrangement of the horizontal and vertical routing channels, so that part is emphasized. So you can see that logic blocks are isolated. Actually, logic blocks has got connection with this one, but to keep the diagram simple, these connections are not shown. You can see that there is a matrix. This is called a matrix, or this is a block. This is called programmable switch matrix, PSM. So this type of PSM was there in CPLD also, programmable interconnect. The name was given over there, but they have got a very similar type of function. So the single lines, they are actually wires. Okay, they are our wire, or you can think them as bus which carry the signal. So they are coming from, suppose output of this. Okay, there is a message coming that our this session will also be expired within after 10 minutes. So if anything is left out, I'll create another session if it permits. Then we will conclude whatever we are intended to discuss in today's class. So let me quickly discuss about the horizontal and vertical routing channels. So so these are wires. Uh, they are connected to this PSM, programmable switch matrix. These are called singles. So these are connected here. From here it is connected to here. From here it is connected to next block, like that. And so is the case of vertical wires also. The singles are connected like this, from here to this block, from there to this block, like that. But here inside this there is switching arrangement. For example, this wire, okay, for example, this wire, okay, you can connect to this wire. You can connect to this wire. Understand? So, so this again I'm taking this wire. This wire can be connected to this wire. So through this PSM. So I will show you how it can be done in the next slide. And there are certain doubles. There are certain doubles, as you can see. So doubles meaning that you can see this wire is connected here in this PSM and it is not connected in the next one, and it is connected in the next one. So that means they are connected in alternate matrices. So if you connect switches, then what will happen? There will be some amount of delay incurred. So there may be requirement that you have to route this input to this block. So in that case, you may have to skip. You can think that this is the arrangement these days in our road. We can see that certain bypasses are being constructed to avoid the congestion in the city. Suppose a truck which need not have to enter Agartala city, so it can be routed from Khayarpur to what is that place called? um, um, Amtoli, Khayarpur to Amtoli through this bypass route, and it need not have to incur the delay or inconvenience of the congestion of Agartala city. If it is going to the south, suppose if it is going to Udaipur, or if it is going to beyond that Sabrum, so in that case, it need not have to waste its time coming inside the Agartala city. So you can think that these lines are certain bypasses which bypasses the alternate PSM, so that the signal can travel quickly if such requirement arises. Now in the next slide, we will go inside this PSM, how this line gets connected with this one and how it can be programmed. See, this is a very interesting, slide. Over here, you can see that this PSM, this PSM is being shown over here. This is one PSM. So this is our vertical lines. These are our horizontal lines. So this is one dot. So this dot is not, showing the fixed line. This dot actually meaning such arrangement. What is this arrangement? This line, this vertical line can be connected to this horizontal line. It can be connected to this vertical line. It can be connected to this horizontal line. You can see the dashed line over here. So through this dashed line, it can be routed to this one, but one at a time. If you want to route it through this one, so through this dashed line, through this line. So here actually fuses are there. Now how does this fuses look like? This diagram is again shown here. See, one such fuse, this arrangement is being shown by this one. So this is a MOS transistor, and this is the gate. In the gate of this MOS transistor, there is a SRAM. SRAM means it's a flip-flop, you can think. So think that this is a D flip-flop. If this D flip-flop is storing a 1, that means this MOS transistor is on. So this line is connected with this one. Under that situation, all other 5 means 1, 2, 3, 4, 5. So all other 5 will not be connected. So this line will be connected to this one. That means this line is connected with this one. That means this vertical line is connected to this one in this junction. Suppose at other point of time you want to connect these two, this line to this line. In that case, only this SRAM will be 1, this D flip-flop will be 1, so that this MOS will be in on state or saturation state, current will flow through this, and all other 5 will be storing a 0, so that they are disconnected. So that means this horizontal routing channel will be routing line will be connected to this line. So this is when we program, we actually store 1 and 0 in these flip-flops, so that accordingly the routing channels are established. I hope you have understood. So this is a simple MOS transistor. It is actually a fuse. That fuse in PLA or PAL we were handling with. So this is how the fuses are actually implemented in today's technology. Now the final topic is soft processor. Uh, I hope I can complete this within this session. Now, soft processor is an intellectual property code. Actually, it is a program. Soft processor is a program written to implement uh, a processor within FPGA or CPLD. So it is intellectual property core, why it is called IP, is that because it is a program, like it is a VHDL program or a Verilog program or some other similar type of program, which has got certain inputs, certain outputs, and it has got processor like structure. Those who know about 8085 microprocessor or similar type of microcontroller, so we can think that the soft processor is also a microcontroller. Okay, so the key benefit include configurability to trade between price and performance, faster time to market, easy integration with FPGA fabric, and avoiding obsolescence. Now these are maybe a little hard terms for you at this moment to understand, but anyway, let me try. See, uh,